allow me to introduce our next speaker, Professor Fatma Abdelhedi from the Faculty of Engineering at King Abdulaziz University. Her current research interests include nonlinear systems, automatic control, network systems, and robotics. Welcome, Professor.
Yeah, for the invitation to the KAUST Research Conference on Robotics and Autonomy 2022. Delighted to be here today and to provide this talk about motion planning mobile robots, especially the force field-based OSF2 method for motion planning. This work is part of a project that I've been involved in the framework of collaboration between the Control and Energy Management Laboratory from the National Engineering School OSFAX Tunisia and the Digital Research Center OSFAX Tunisia. This work is a collaboration with Professor Mohammed Jah and Dr. Safa Ziadi from the University of OSFAX. Let's start here by giving a brief bio. At King Abdulaziz University at the Electrical and Engineering Department at the Faculty of Engineering. I received my PhD at the National Engineering School OSFAX on March 2016. I held the assistant professor position at the High Institute of Industrial Management of OSFAX Tunisia and conducted postdoctoral research with ANPR, the National Agency for Research Promotion, funded by the European Union in the robotic fields. So from the great world of robotics, solutions are emerging to mitigate the impact of the pandemic, which has affected several sectors. This impact has a great impact on the awareness and increased the awareness about the necessity for automation and robotics in several sectors such as industry, healthcare, agriculture, and so on. So here, many decision makers have encouraged the development of these fields by providing fundings on these regarding the automation and robotic fields. So as I said before that the work I'm presenting is part of a project which is entitled Autonomous Robotic System for the Transfer of Fruit Crates in the Agricultural Field. This project focuses on the design and fabrication of wheeled mobile robot prototype carrying a dual arm manipulation and includes solar panel for the storage of photovoltaic energy in a reliable battery, which will make the whole system autonomous. It involves several research axes such as manipulator arms, energy autonomy, and mobile robots. Here as a fast-growing research field, so mobile robotics are fast-growing in the market. Here I present infographic about the mobile robot market on 2022 based on a recent report of Interact Analysis platform. This report presents and shows the rapid increase of the pace of development of this field in 2022, as it was just worth $1 billion in 2017 and is forecast to hit $7 billion in 2022. Okay, so as a fast-growing research axis, here the mobile robots are facing challenges such as autonomy and safety. Here, the autonomy refers to the ability of the robot to act autonomously and take its own decisions. Safety refers to the ability of the robot not to harm itself, persons, and to act dynamically even alongside humans. Navigation also presents an important challenge in mobile robotics, which refers to the ability of the robot to maneuver independently in its environment from a start to an end location. In particular here, navigation is based on three main parts, which are the localization, mapping, and planning. Localization here refers to the ability of the robot to determine a precise position in its workspace, depending on, for example, the data collected from its sensors. Mapping means the ability to create a map in its environment. And planning refers to the ability of the robot to find or to the search of the free collision path from a start to a target location. Planning here can be classified as a multi-objective optimization problem, which is based on the collision avoidance, less distance, time travel, and to reach the destination. And all these factors depend from the environmental complexity. Okay, so several approaches in the literature have been used. There are approaches that take into consideration the robot's dynamic and kinematics constraints, such as the curvature velocity method, the vector feed histogram, and other approaches didn't take these constraints into consideration, such as the artificial potential field. Here, the advantage of the force field method is that it's a real-time collision avoidance approach, which is suitable not only for single robot, but also for multi-robot motion planning. There are designs derived from F2, such as canonical force field and the dynamic variable speed force field, the DVSF2. Here, as a real-time collision avoidance approach, F2 is defined as a virtual field of repulsive forces in the vicinity of a robot when it is moving in a working space. So this approach contains two main forces here, which are the repulsive and the attractive. The repulsive force is a virtual one, which is applied by the obstacle on the robot. So when the obstacle is included in the area, force field area of the robot, so it will be influencing the movement of the robot by applying virtual repulsive force on it. The attractive force here is a virtual force applied by the goal on the robot, so to drive the robot toward its goal. Here I have a figure describing the main concept of the F2 approach. So here presented the robot, its goal, and the existing obstacle, which is included in the force field area of this robot. In fact, the force field area here is limited by the Dmax and Dmin circles. The Dmax, the green circle here, presents the maximum action distance at which the obstacle will apply a minimum repulsive force on the robot. And Dmin here is the minimum distance at which the obstacle will apply the maximum repulsive force on the robot. So if the obstacle approaches to the robot and it's near to the minimum distance, so its repulsive force will be increasing, and at the level of the minimum distance, it will be applying its maximum repulsive force, so to repel the robot, and the robot here will be in its maximum deceleration, so to avoid collision as the obstacle is too close to the robot. The point A here is the nearest point on the obstacle to the robot, so at which the repulsive force will be applied and directed to the center of the robot. The magnitude of the repulsive force here depends on the robot speed, the robot size, and also the distance between the obstacle and the robot. So for example, if the obstacle is included in the force field area, so it will be impacting, as I said, influencing the behavior of the robot by exerting these repulsive forces. I can illustrate with the example of a robot which is moving in an obstacle cluttered environment. So this robot will have its force field, which is smaller, and also its speed will be decreasing, so to allow the robot to pass through narrow passages. Here in this figure, just the position of the obstacle is closer to the robot, and I can note here that the force field area depends on the robot physical characteristics, and also on its speed. So if the robot move faster, so the force field area will be larger, so to provide a sufficient space to the robot for deceleration and also for steering away obstacles. And if the size is larger, also the force field area, coverage area, will be also larger. Here the expression of the force field forces are presented. Here we have the repulsive force applied by the obstacle on the robot, which is depending on Dmax and Dmin, which are the limits of the force field coverage area. And here I have the repulsive and attractive force expressions. Okay, now I move to the design deriving from the force field approach, which is the dynamic variable force field approach. Here it is characterized by the fact that the evolution of linear and angular velocities depends on the sum of the attractive and repulsive forces. For example, here we have the expression of F total, which is the sum of the attractive force and the sum of all the repulsive forces which are applied by all the obstacles included in the force field area of this robot. Here we have the expression of the angular velocity and the linear velocity, which are depending on F total and the maximum repulsive force. And this will yield to improve flexibility of the robot in its motion. This method has the advantage that it's suitable for real-time collision avoidance in a dynamically changing environment with unexpected obstacles. Okay, so here to investigate the selection of the parameters on the performance of the DVSF2 method, PSO, the particle swarm optimization algorithm, is used for the search of optimal parameter selection of our proposed approach. Here, as brief introduction for PSO, it is inspired from the social behavior of birds flocking. So the displacement of birds from one place to another is equivalent to the evolution of the swarm of solutions. Here, each particle in the swarm is characterized by its position and its velocity. So each particle position here is depending on the current position and velocity, the distance from the personal best attempt of the particle, and the distance from the global best performance of the swarm. Here, regarding the speed, so each particle adjusted according to its experience and to the social experience of the swarm. The goal here is to find variables that minimize the objective function while satisfying constraints. So our fitness function here is a weighted sum of two criteria. The first criteria is to minimize the travel length between the position of the robot and its target. And the second criteria is to maximize the distance between the robot and the nearest obstacle. Here I have the vector xi, which includes the optimized parameters, which are relative to the parameter delimiting the coverage area of the robot, the parameters adjusting the magnitudes of the repulsive and attractive forces, the environmental parameter, which is measuring maybe the effect of the environment on the force field area, and the parameter which determines how close can the robot be to the obstacle. Arriving now to the PSO-DVSF2 algorithm simulation results in static and dynamic environments. Here we have static environment where we have the blue circles are the static obstacles, and here are static obstacles also. And here we have the start and the goal of the robot. The generated path is presented here, which is presenting satisfying performances regarding the collision avoidance and also regarding the optimization of the path. Regarding the dynamic environment, we have same performances are presented where we have here the dynamic obstacle presented in the green. So the robot travels from the start to the goal, and it is, as I said before, that it is satisfying collision avoidance with obstacles and the optimization of the path. But the drawback here is the appearance of oscillations in the trajectory of the robot in its path, mainly when it is avoiding obstacles, when it is near to the obstacles. So there are oscillations which are reflected here in the angular speed variation with the high and rapid oscillations, which are disturbing the smoothness of the robot trajectory and making yielding the instability for the robot in some parts of its trajectory. So we can assume that PSO-DVSF2 algorithm gives good or satisfying performances regarding collision avoidance and optimization of the path, but its major drawback that the rapid and high oscillations appearing on the angular speed variations, which are affecting the global quality of its generated path. Okay, here, so we are searching for solution to overcome this drawback. We present here in a first step, we will impose the angular speed limitation on the DVSF2 approach. So we will try to limit the oscillations and to avoid these disruptions to improve stability of the robot. Then in a second step, the optimization will play its role in search for the best combination of the optimized parameters for the SF2 and which will yield the optimized and stable F2 algorithm. Here we can note that the xi, the vector containing the optimized parameters, includes also here the omega max, which is the maximum value of the angular velocity, to be considered as an optimized parameter also. Okay, so after these updates, so the OSF algorithm is its simulation results is presented here, where we have the generated path of the robot after application of the OSF. Here we have the two dynamic environments, the first one containing only one dynamic obstacle, and the second one contains two more complex. So here we can note the trajectory of the robot, which is avoiding collisions, optimizing the path, and also in addition to the improvement of the stability of the robot, even in the presence of obstacles. So the disappearance of the deviations, rapid deviations in the behavior of the robot is noted here. And this is due to the updates and to the application of the angular speed limitations on the angular speed of the robot. Okay, here I can resume. I say that the collision avoidance and optimization of the path are always guaranteed, and in addition to the improvement on the smoothness of the trajectory and the quality of the travel of the robot. Here I have additional simulation results which are proving also the same performance of the OSF2 in comparison with PSO-DVSF2. I move now to the summary. So finally, as I focused on the performance and the importance of the motion planning in mobile robots, so OSF is presented here as an improved solution to ensure better trajectory smoothness, in addition to the optimization of the travel distance and also to the collision avoidance. So this method is under development and practical implementation in the framework of Franco-Tunisian collaboration with LISV laboratory from France. And our next perspectives here is to consider that there are important challenges on which we will focus. The first is to continue development and practical implementation till the practical test of the approach, and then to work on the real-time search for the optimal path in dynamic multi-robot environments, where the robot has to deal with uncertain position information and disturbances. That's it for me, Doc. So thank you very much, and your question.
Thank you very much.
What's the value of the mobile robots market in Saudi Arabia?
The statistics I presented wasn't for the Saudi Arabia only; it was just in the world. So what I know is that the mobile robots are always in the increased demand in all the almost all the countries, as it is very important. And as I said, that after the pandemic, there are very demand for the or necessity for the automation and for robotics, especially the mobile robots.
Thanks for the talk. I thought it was really useful, and I especially liked your example of the flocking behavior. That was kind of a cool implementation of that. So that was nice. I was looking at the last graph though, where you were basically trying to get rid of the chattering behavior. And I was wondering if you basically had looked into some of the other kind of tools that you might use, like using, like a dead zone or something in order to keep it from oscillating too much. Because it kind of seems like just restricting the oscillation has an effect on, your ability to get your maximum control range. It keeps you from being able to turn as sharply when you restrict your maximum omega. I'm wondering if there's maybe a different algorithm that you've looked into, or if there's any further work in that, because I think that there are ways that you could just kind of drift back and forth rather than having the high oscillation.
If I understand your question, so the advantage of this approach is that here the orientation, for example, of the robot, it is in the absence of obstacles. The robot is attracted by the attractive force applied at the robot by the goal, the virtual attractive force. In the presence of obstacles, so the orientation will be the sum of all the forces applied on the robot. So here, sometimes the repulsive forces, when it is it become greater than the attractive force, so there will be the deviation. And so here, to allow the robot to avoid obstacles. So here, the deviations in the presence of maybe more than one or two obstacles will be affecting clearly and badly maybe the behavior of the robot. For this reason was the idea to limit the angular velocity.
Assalamualaikum warahmatullahi wabarakatuh. Thank you so much for Professor Fatma about the presentation, interesting presentation. So I have question about how about the accuracy real-time search for the optimal paths in dynamic multi-robot environments?
Yes, in the dynamic multi-robot environment. So this is considered as next point to be studied. But here in the multi-robot environments, there are several robots to be interacted between them. So there are communication, and there will be also the study of priority between robots. If two robots are in the same point or going to the same point, so there are, for example, the which of these robots will pass the first, and the priority here will be also studied. And many also points that consider the multi-robot environments.
Thank you very much.